Hey, welcome back. In this video, we're going to discuss planar graphs, which are a special type of graph that can be drawn in the plane so that no edges intersect except at the vertices. And there will be multiple ways to draw planar graphs with this property that none of the edges intersect except at the vertices. Any drawing with this property will be called a planar embedding of the graph. So first, I'd like to start out just by drawing some planar graphs and some planar embeddings as well as non-planar embeddings. The first graph we can look at is K3. We've seen this one a lot, the triangle. And the way that we usually draw it is already a planar embedding. Another graph that we've seen sometimes is K4, complete graph of order 4. And usually when we draw that one, we have 4 vertices arranged in a rectangle. And then we draw the other 2 edges intersecting in the interior of the rectangle. That would not be a planar embedding. However, K4 is planar. So K4 has a planar embedding. It's just that the way that we have normally drawn it is not planar. And it's similar with K3. You can draw K3 in a non-planar way. So here's a way that we could draw K3 that would not be a planar embedding. We take these 2 edges, and then the last edge we draw like this. That would not be a planar embedding, but it's still a K3. For K4, if we want a planar embedding, we can start with how we would draw the K3. And then we can put the 4th vertex anywhere besides the edges or the vertices. So on the outside or the inside, put on the outside for now. And these edges we can add and keep it planar. The last edge, we can't put it through the center because that would turn it non-planar, but we can put it around the outside. And that gives us a planar embedding of K4. Anytime you have a planar embedding of a graph, you always will have infinitely many planar embeddings of the graph. So of course you can rotate it around, you can dilate or contract it, you can move vertices around a negligible amount. So there's many different planar embeddings of a given planar graph. For K4, here's a slightly nicer looking planar embedding. If we put the 4th vertex in the center of the triangle, we can make all of our edges line segments, so that's a little nicer looking, and still a K4. In all of those pictures that we saw on the last slide, in all of the planar embeddings at least, we had vertices, we had edges, and we had a third thing called a face, which is a maximal region of the plane with the property that for any 2 points in the region, you can join them by a curve, and that curve must intersect no edge of the embedding. To illustrate this definition of a face, let's consider a few different pictures. Let's start with the K3. And we have our standard drawing of it. One face is on the inside here. I'm going to draw its boundary. It's the interior of this triangle. The inside within the 3 edges. So that's one face. And we can notice if you have any 2 points in here, we can join them by a curve that intersects no edge of the embedding. We also have a face out here. I'm going to draw its boundary with some lines. You should visualize these lines I'm drawing as being infinitely close to the edges. So here's our outer face. If you have any 2 points out here in the outer face, we can join them by a curve that intersects no edge in the embedding. Point here, you can do the same kind of thing. So that's K3. We have 2 faces there. We can do something similar with K4. So with K4, we put some vertex on the outside. We have a face inside here. We have a face inside there. So their boundaries I'll draw. And you should picture these as much closer to the edges. This one, I'll draw its boundary. Should also be pictured as much closer to those edges. It's a face. And also, we have this outer face. So we have a total of 4 faces in this K4. We see this outer face, any 2 points on the outside. You can join them by a curve which intersects no edge of the embedding. Let's consider one last example for now. We'll take a K3 and then we'll join a leaf to it. So still we have the face on the inside. And now we have this outer face, which is shaped a little different than the K3. Its boundary at least. And with this outer face, you have any 2 points on this outer face. You can join them by a curve that intersects no edge of the embedding. So we have 2 faces there, just like with the K3. And with all of the faces, we can define their length. The length of the face is just going to be the number of edges on the boundary. So for example, with this outer face, its length is going to be 3, and the inner face is going to have length 3 as well. They both have 3 edges along their boundary. Now, let's look at this picture. Each of these inner faces will have length 3. They all have 3 edges on their boundary. Same with the outer face. It also has length 3, 3 edges on its boundary. So length 3 for all on the K4. Now, the interface with this graph on the left, it has length 3. So I put my 3 there. The outer face, let's count that. So let's start from up here. Well, let me not write it there. So let's start from the actual vertex. So here's the vertex. And then let's count how many edges we have to go through to get back to this vertex. So we go 1, 2, 3, 4, 5. So the length of that face is going to be 5. So the number of edges along the boundary, when we draw that boundary, we had the 1, the 2, the 3, the 4, and the 5. So the first and last edge were from the same edge, but when we went along the boundary, that was 2 edges along our boundary. We counted it twice specifically. So the length of this one is 5. I'm not sure why I wrote it down there, but yeah, should be 5 up there for that outer face. And one other thing I want to note, so you can see from all these pictures, all 3 of them had an unbounded face. The unbounded face is just the outer face. Now, anytime you have a planar graph, you have some planar graph, you draw it as a planar embedding, you can take a rectangle that is outside, or that contains all of the vertices and the edges. So any edges in our planar graph are contained inside this rectangle. And the face that's outside the rectangle, so the face that contains the region of the plane out here, that's going to be the unbounded face. So that's how we know that every planar embedding of a planar graph has an unbounded face. So we can say every single one, because we can always take a rectangle that's sufficiently large that it contains all the vertices and all the edges. And we know that the region of the plane that contains the exterior of that rectangle has to be our unbounded face. So the maximal region of the plane that contains that rectangle. And another thing I want to note, and this is something that we've already seen on the first slide, with both of the graphs that we drew, the K3 and the K4, we saw that they can have multiple planar embeddings. So any planar graph can have multiple planar embeddings. Like I said, you can rotate things, you can contract or dilate, you can also move vertices around a small amount, and this is going to not change it from being planar to non-planar. One thing that's going to stay the same when you draw different planar embeddings of the same planar graph is going to be the number of faces. So the number of faces, regardless of what planar embedding you draw of your planar graph, it will always have the same number of faces. So any planar embedding of K3 will have 2 faces. Any planar embedding of K4 will have 4 faces. And any planar embedding of that graph that I drew on the left, the K3 with the added leaf, that will have 2 faces. And in general, we can give a pretty simple formula for the number of faces in terms of the number of vertices and the number of edges. It's called Euler's Formula. And we're going to prove it in this video for connected graphs. And I'm going to leave it as a problem to you to figure out what the formula should be more generally for any graphs, including disconnected graphs. Here's the formula. For every connected planar graph G with order n, m edges, and f faces, we have the equation n minus m plus f equals 2. So the problem for you is to determine how should the formula generalize to all graphs. So not just connected. And it would make sense to write your formula in terms of the number of connected components in your graph. So we're going to prove Euler's formula for connected planar graphs. And I'll leave it to you to determine how we should change the formula in terms of the number of connected components for any graph, even if it's disconnected. So let's see the proof of this for connected graphs on the next slide. In order to prove this, we're going to use strong induction. And the strong induction is going to be on the number of edges. So it's going to be on M instead of N. And we're going to start just with empty graphs. So graphs with 0 edges. And we're going to use the useful fact here that our graph is connected. And we'll assume that we're not dealing with a graph that has no vertices. So if we have no edges and a connected graph, then that means it has exactly one vertex. So again, we're not assuming that the vertex set is the empty set. So we're not dealing with graphs with no vertices. We're dealing with graphs with some vertices, but there's no edges. So if there's no edges and it's connected, there can't be multiple vertices. There can only be one vertex. And if we have a graph with only one vertex, if we count the number of faces, well, there's no edges, and the face is just everything out here. So that's a face. So any 2 points out there, we can connect them by an edge, by a curve that intersects nothing in our embedding, because our embedding is just that point right there. So the n equals 1, the order is 1, f equals 1, the number of faces is 1, and the number of edges is just 0. So we get 1, 0, 1, and that gives us 2. So in the base case, this formula is true. And now we're going to do the strong inductive step. So we have a strong inductive hypothesis. We'll assume that the formula is true for any connected planar graph with at most k edges. So this formula up here, we're assuming that that's true, this formula, for any connected planar graph with the most k edges. And regardless of what its order is, whatever the n is, whatever the f is, that formula will be true, as long as the number of edges is at most k. And we need to prove that the formula will be true when the number of edges equals k plus 1. So that will be the inductive step. We'll be getting k plus 1 using all the values up to k. In order to do that, we just need to take some arbitrary connected planar graph with k plus 1 edges. So the most important piece of information about this graph G, is that it has k plus 1 edges. Besides the fact that it has k plus 1 edges, we'll also give a name to its order and its number of faces. We'll say it has order n and it has f faces. But again, I just want to emphasize the important information here is the number of edges. That's k plus 1. And we're going to prove that the formula up here must be true for G. And we're just going to use this n and this f in order to write some quantities in a shorter way. So we're going to split the proof into cases. There will only be 2 cases. Our first case will be when G has a vertex of degree 1. And our second case will be the opposite of that, when all of the vertices of the G have degree not equal to 1. So for this first case, when we have a vertex of degree 1, when we have our planar embedding of G, so we have some G here, and we have some vertex of degree 1. Here's our vertex of degree 1. It only has a single neighbor because it has degree 1. If this is our graph G right here, in order to get a new graph G prime, we'll construct G prime just by taking the original G. So there's G. And we're just going to remove the vertex of degree 1 and the edge that contained it. So that's G prime. So all we did is we took out the vertex and we took out the edge containing the vertex. And we can note that G prime is still going to be connected. So if you take out a vertex of degree only 1 from a graph, it can't disconnect the graph if the original graph was connected. So to disconnect the graph, you have to take out a vertex of degree at least 2. So if you take out a vertex of degree 0, or you take out a vertex of degree 1, this won't disconnect it. You can think of it like, in order to disconnect a graph, when you remove the vertex, there have to be multiple parts left when you take that vertex out. So the vertex has to have multiple neighbors in order to have multiple parts left when you remove this vertex. So it can't have degree 1 to have multiple parts left. So if it has degree 1, when you remove the vertex, there's only one part left. And the original graph was connected, so that part is going to be connected. So G prime, that's why it's connected, because we removed the vertex of degree 1, so we can't disconnect it that way. And it's still going to be planar, because all we did is we took our planar embedding and we took an eraser, and we just erased that vertex right here. We erased this edge right here. Erasing a vertex and an edge in a planar embedding, it's not going to make it non-planar. Erasing edges, all that can do is possibly make it planar. It can't make it non-planar. It only helps it become possibly more planar. So G prime is connected and planar. Now we removed a vertex from G to get G prime. G had n vertices, so G prime has order n minus 1. We also removed an edge from G to get G prime. G had k plus 1 edges, so G prime has k edges. And we see that when we remove a vertex of degree 1, like we did here, we don't change the number of faces. So here, this outer face, as I've drawn it, and here's the outer face as I've drawn this. And the outer face, the boundary looks different, but the number of faces stayed the same here. And we might have a situation where the vertex that we remove is on the inside. So maybe we have some leaf right here on the inside, and then that's our G, and then the G prime looks like this. And we got rid of that vertex. And that we see also has the same number of faces. So the interior face here has this weird shape. And just picture these lines I'm drawing being closer to the actual boundary on the inside. And the shape here is less weird, but we still have the same number of faces there. So we can use our inductive hypothesis on G prime because it has k edges. And our inductive hypothesis applies to any connected planar graphs with at most k edges. So I should have underlined that one. So the inductive hypothesis was that the formula is true. So the order minus the number of edges plus the number of faces has to equal 2. So n minus 1, the order, minus the number of edges, k, plus the number of faces, still f, has to equal 2. And we can rearrange things. We can take the 1 and the k, and we can group them together into here as a k plus 1. So we write that as n minus quantity k plus 1, and then plus f equals 2. And that's exactly what we wanted. So we showed the formula is true for G. And G was just an arbitrary connected planar graph of order n with k plus 1 edges. So an arbitrary connected planar graph with k plus 1 edges, because the n was not important, nor was the f. So any connected planar graph with k plus 1 edges, as long as it falls under case 1, the formula will be true for it. So now, since we proved case 1, we only have to prove case 2, which is the opposite of case 1. So for case 2, we will assume that G has no vertex of degree 1. And I'm just going to underline the important piece of information again, that G is connected. So if G has no vertex of degree 1 and G is connected, G also has no vertex of degree 0 since it's connected. So no vertex of degree 0, no vertex of degree 1, it means all the vertices have degree at least 2. So the minimum degree is at least 2. And earlier in this class, we saw this result when we were talking about degeneracy. So we said that any acyclic graph is one degenerate. In other words, every subgraph of an acyclic graph contains some vertex of degree at most 1. So the fact that G has minimum degree at least 2, it has no vertex of degree at most 1. This means that G cannot be acyclic. So if G is not acyclic, that means that G has a cycle. So since G has a cycle, we can look at G. We have some cycle in it. And we'll name one of the edges on the cycle. We'll call it E. And I'll draw it again down here. Try to draw it kind of similarly. Okay. And that would be G prime. And G prime will be obtained from G. So right now it looks like G, but we'll do something to G to get G prime. So that edge E, in order to get G prime from G, we're just going to remove the edge E. So we'll erase right there, and I'll have to draw the other edges back in there. There, okay. So when we remove that edge, let's look at what happens to our graph. So first, we see that the graph remains planar for the same reason as in case 1, the G prime remained planar. That's because if we have a planar embedding and we erase an edge, it can't make it non-planar. Erasing edges can only help us become more planar. So we erase an edge, our graph will still be planar, and we still have a planar embedding. Moreover, we erase an edge from a cycle. If you erase an edge from a cycle, the graph must stay connected. So if you start with a connected graph, you erase an edge from a cycle, this is not going to leave you with multiple connected components. So the only way to be left with multiple connected components is if we delete some edge. So we have some edge right here. And when we remove that edge, we would need these two components right here not to be connected to each other. But this edge is part of a cycle. So those components actually do have to be connected to each other. So if you remove an edge from a cycle and you have a connected graph, removing that edge still leaves you with a connected graph. So G prime, it's both connected and it's still planar. And we can also see that since we only removed an edge, we didn't remove any vertices. So the number of edges is going to be 1 less. So that's going to be k edges compared to k plus 1. Maybe I will move that over if I can. Let's see if I can do that. Okay, so the number of edges, k, is just 1 less because we removed the edge. The order is the same, order n, because we didn't remove any vertices. And we can see what happens with the number of faces here. So when we take that edge out, we're breaking the cycle. So that is destroying exactly one face. So the number of faces here went down by exactly 1. So we originally had f faces. Now we have f minus 1 faces. So in the way that I've drawn this picture, we had 2 faces up here. We removed that edge. We only had 1 face. So here we just have this outer face. And down or up here, we had 2 faces. We had the outer face and the inner face. So if we remove an edge from a cycle, we decrease our number of faces by 1. So we have f minus 1 faces. And we can use the inductive hypothesis here again. So our inductive hypothesis applies whenever the number of edges is at most k. So we have k edges here. And that means that we have the formula, the order minus the number of edges plus the number of faces equals 2. So n minus k plus f minus 1 equals 2. And we can rearrange things. We can join the k and the 1 together. So we get n minus the quantity k plus 1, and then plus f equals 2. So this finishes the proof of Euler's formula for connected planar graphs. And again, to generalize it to all graphs, including disconnected ones, that proof is left to you. But you can use the formula for connected graphs in order to get the formula for graphs in general. Now, if we have a planar graph where we can't add any more edges to it, we call that a maximal planar graph. So for example, here's one that is trivially maximal. We can't add any more edges to that. Here's another one that will be maximal. So these are both complete graphs. So we can't add any more edges to them. Now, what if we have a K4 and then we add a 5th vertex? So we take edges to these 3. And then the question is, can we put in that last missing edge? So it'd be nice if we could somehow fill in that there and get our full K5. Can we do that? So can we get a K5? Or is the one I drew maximal? So if we add in that edge between these two, will that make it non-planar? So that's just to illustrate this definition. So a planar graph is called maximal if adding any edge to the graph makes it not planar. So these first two, that's maximal, as is this one right here. And maybe this one is too. So we'll see. We'll see soon a way to determine if it is. So another way to see if a planar graph is maximal instead of just the definition, you can see that this definition is equivalent. If you have a graph being maximal, this is equivalent to each face being of length 3. So why is this true? Well, let's say you have some face with more than 3 edges on it. So here's some face with more than 3 edges. So this interior face, the way I drew it. So we're considering the face on the inside. So I won't draw the whole. Well, maybe I will draw the inside, but then I'll erase it so we can draw something inside. So the interior face is what we're considering here. So if this one has a length greater than 3, like the one I drew, we can just start connecting vertices inside the face like this. Now, all the inside faces have length 3, but that outside face has length greater than 3. How can we deal with that? Well, we can put an edge here, an edge there, an edge here, an edge there, and then let's do one more around this side and squeeze it past the 3. An edge here. And then, let's see. So let's look at what we have here. So each of these faces, we can see that, oh, it looks like I drew some extra edge in there. So let's see. So we had our original. Okay, so this is our original graph right here. Yes, I did draw an extra edge. Okay, I think that fixes it. So now we can look at all our faces. So this face right here, this one has length 3. This one also has length 3. Even though the way I drew is weird, we can count the number of edges on it. We got 3 there. Same with this one here. So that one has 1, 2, 3. Same with this one. 1, 2, 3. And then we have some other faces we can look at. So here's a face of length 3. There's another face of length 3. There's one of length 3. Here, here. And then let's see. We have 1. Then this one goes all the way around to 2. And then 3. So that outer face also has length 3. So you can see if you have any planar embedding and it has some face with more than 3 edges, you can just keep on adding edges to your planar embedding to make it maximal. And when it becomes maximal, every face is going to have exactly 3 edges on it. So every face will have length 3. And of course, what I drew here is just an example. It's just a drawing. But the method that I did in that example, you can use that for any planar embedding. So I'm going to clear a little bit so we can see more bullets. So here's a claim. And we can prove this just using the definition of maximal planar graphs. And the claim is that the number of edges in a maximal planar graph of order n is going to be exactly 3n minus 6. How to prove this? We'll just take a maximal planar graph of order n, and we'll assume that it has m edges and f faces. And we're going to try to use Euler's formula here. We're going to also use this property that we just discussed, that if we have a maximal planar graph, every face is going to have length 3 in any planar embedding. So using that property, we can see since G, this graph is maximal, every face has length 3. In other words, every face has 3 edges. And moreover, we can say that each edge will bound two faces. So if we have our maximal planar graph here, I'll draw one. So here's a maximal planar graph. So we can see every single edge, it bounds two faces. So this edge right here, between this one and this one, that edge bounds this face and this face. This edge right here bounds this face and this face. This edge here bounds this face and this face, and so on. So all the edges bound two faces. And we can do that for any maximal planar graph. So any maximal planar graph, it's clear that all of the interior faces have length 3. And we know not just that, but the exterior face also has length 3. So we saw you can take any planar graph here. We fill the inside with triangles. And then we can make the outside also have length 3. And the outside totally has length 3 there now too. So 1, 2, 3. So every face has 3 edges, and each edge bounds 2 faces. So clearly, any of the edges in the interior bound 2 faces. And the edges on the exterior, they also bound 2 faces. They're going to bound, each of them will bound an interior face and the exterior face. So any of the interior edges will bound 2 interior faces. So this tells us if we take the sum over faces f, so we'll say faces script f of the number of edges on the boundary of f, so number of edges in f, we'll say. So the length of f, we could have written it as. That's going to equal 3 times the number of faces, so 3f. It's also going to equal 2 times the number of edges, because when we look at this sum, each edge is going to occur twice in that sum, because each edge bounds exactly 2 faces. So that's why we get 2m equals 3f. And we can plug that into Euler's formula. And we're applying that because this graph is connected, because it's maximal. So we know if it was disconnected, we could keep on adding edges to it till it's connected. So we have a connected planar graph. We can apply the Euler's formula that we proved for connected planar graphs. And since we know that 2m equals 3f, we can say that f equals 2/3 m. So we substitute that in to the Euler's formula, and we solve for the m to get m equals 3n minus 6. As an immediate corollary, we see that any planar graph of order n has at most 3n minus 6 edges. So if you have a planar graph of order n, you can just keep on adding edges until you make it maximal, like I did with this example right here. And we know that the number of edges in the original graph has to be at most the number of edges you get when you turn it maximal. And the number of edges you get when you turn it maximal is going to be 3 times the order minus 6. So that's how you get this corollary immediately. And I have a problem for you to think about. And the problem is just to prove or to disprove that planar graphs are 5 degenerate. So we're also going to look at a slightly more specific family of planar graphs, the bipartite planar graphs. And we can imitate the method that we used in the last proof to get an upper bound for these bipartite planar graphs, an upper bound on their number of edges. And this upper bound we get is 2n minus 4. So let's look at how to prove this. And we'll try to imitate the method we just used in the last proof. So we'll suppose that G is any bipartite planar graph of order n, which has m edges and f faces. So clearly, just like the last one, we're going to try to use Euler's formula here. But we can say a little more about the number of edges in the face now. So if we have a planar embedding of our graph, we know that a bipartite graph, so bipartite, that means no K3. So you can't have any triangles in a bipartite graph. You can't have any odd cycles in a bipartite graph, but we're only going to use the triangle part here. So since it's a bipartite, it has no K3. And that means that any face in the planar embedding must have at least 4 edges. So faces in general must have at least 3 edges. But if there's no K3, then every face must have at least 4 edges. So we can look at, again, the same sum that we were looking at with the last one. The sum over the faces f of the length of f, so the number of edges in f. I'll just write it as the length this time. And we can use that sum to get an inequality. So I claim this sum can give us the inequality 2m is greater than or equal to 4f. So first, if we look at the sum over the faces of the length of f, we know every face has at least 4 edges. So this sum is going to be greater than or equal to 4 times the number of terms in the sum. Number of terms in the sum is just the number of faces. So we get it's greater than or equal to 4f, f the number of faces. Now, we also know that every edge bounds at most 2 faces. So this sum is going to be less than or equal to twice the number of edges. So why is that? When we look in this sum, each edge is counted at most twice. So each edge is counted in that sum at most twice because each edge bounds at most 2 faces. So that tells us that 2m is greater than or equal to 4f. And we can use this, so we can say then that the f is less than or equal to m over 2. And we can use Euler's formula here. So Euler's formula tells us that m equals n plus f minus 2. And we can substitute for the f. So the f is less than or equal to m over 2. So n plus f minus 2 is less than or equal to n plus 1/2 m minus 2. We can subtract the 1/2 m from both sides and then multiply both sides by 2. And that gives us m less than or equal to 2n minus 4, which is 2 times the quantity m minus 2. So that gives us this bound. So this bound 2n minus 4 is less than the bound we got in general, 3n minus 6. So it's n minus 2 less than that one. And that's because we're only looking at bipartite planar graphs here. So here's a problem for you to think about. Determine whether or not the complete bipartite graph with both parts of size 3 is planar. Also determine whether or not the complete graph of order 5 is planar. And that brings us to the end of this video. Thanks for watching.